Hello, everyone, and welcome to today's event on the topic of enhancing business operations with machine learning. This event is produced by IEEE Educational Activities in partnership with the IEEE Computational Intelligence Society. My name is Jennifer McLean. I'm Senior Manager of Education Products with IEEE Educational Activities, and I will be helping to moderate today's event. IEEE is the world's largest technical professional organization dedicated to advancing technology for the benefit of humanity. Please note a few housekeeping items before we get started. At the bottom of your screen are engagement tools that are resizable and movable, so you can move them around to make the most out of your dashboard space. If you need technical support, click the yellow question mark at the bottom of your screen or type your issue into the Q&A window and our technician will assist you. If you have questions for today's presenter, you can submit them through the Q&A widget on your screen or click the purple Q&A icon at the bottom of the screen, and we will answer as many questions as time allows. To receive a certificate of participation for this event, remember to click on the certificate icon at the bottom of your screen. And finally, the on-demand link for today's event will be emailed to all registrants approximately 2 hours after we finish, and the slides from today's event will also be available to you. If you would like to tweet about this, please use the hashtag IEEELearn. Our presenter today is Grant Scott. Grant is an assistant professor in the Electrical Engineering and Computer Science Department at the University of Missouri and faculty member of the Institute for Data Science and Informatics and the Center for Geospatial Intelligence. We welcome Grant, and at this point, I will turn it over to you.
Hello, and welcome to our webinar today. I'm happy to be here to discuss how machine learning can enhance business operations with how machine learning can enhance business operations. So as we dive in, before a business can begin to leverage machine learning techniques, it must first have an in-depth and broad understanding of its enterprise data. Business data volume is growing at an exponential rate. The velocity and variety of sources for this data is unprecedented and includes traditional enterprise resource data, operational data, extended data such as government and social media derived data, and massive amounts of digital trace data. Businesses must fully appreciate the veracity of some of the data sources as well as accommodate the variability of data from certain sources. All of these big data concepts, volume, velocity, variety, veracity, and variability, can lead to value, especially when machine learning is leveraged in business operations. We have all likely heard the phrase that data is the new oil, implying that if we can properly refine our data from various sources, we can create significant business value. All this raw data must be refined to enhance its usability, interpretability, and value to the company. Traditional business information, such as reports and key performance indicators, or KPIs, are not enough in today's data-driven society. We must push beyond information into business intelligence. Business intelligence, empowered by machine learning, enables more than just forecasting. It enables business decisions that increase productivity and positive results, such as increased sales, optimized operations, and profits. Businesses must develop a data analytics cycle with techniques for deeply understanding the data and key performance indicators of business operations. Developing machine learning models and then evaluating business decisions enhanced by these models to understand their impact on the businesses is key. Predictive and prescriptive analytics empowered by machine learning are key to the cycle. And business leaders must understand how to interpret information from machine learning engineers and data scientists when determining company strategy for machine learning deployments. Machine learning enables predictive analytics, in essence, predicting the future, And then prescriptive analytics allows business leaders to make informed decisions that positively shape that future. Business process automation is a key example of how predictive and prescriptive analytics are changing the industry. For example, we are witnessing the slow rollout of self-driving vehicles. Long ago, the automotive industry deployed cruise control, which evolved into adaptive cruise control powered by sensor systems that allow cars to detect vehicles and adjust the speed up and down. We have also seen the emergence of other smart sensor technologies such as automatic emergency braking and lane keep assist. These examples of human-machine teaming show the path that machine learning can play in various ways of optimizing processes, but not just the mechanical ones. Even workflows and human-centric business processes can be augmented and enhanced with machine learning. At its core, machine learning is the concept of using computer programs and machines to learn to perform a task through exploration and exploitation of data. Businesses must create an enterprise data and cyber infrastructure posture to accommodate machine learning that includes understanding the data layers, relationships in those data layers, and the sources of the data, understanding software tools for data carpentry and exploration, and machine learning, and understanding machine learning models, including their strengths, their weaknesses, and the optimal alignments of models with the particular data, and understanding computing systems that enable scalable machine learning. The data analytics loop is a key concept for fully understanding and exploiting enterprise data. This includes descriptive analytics and data mining to understand what has happened in the past and its effects on the business. Then the ability to understand the point in time or current state of data and the business using diagnostic analytics. Once we understand the past and can know the current state, businesses can develop predictive analytics to understand trajectories, trends, and future outcomes. Machine learning empowers business to change the future with prescriptive analytics. Then, after the business decisions have played out, we return to the first step to understand what happened and its effect on the business. Machine learning is a powerful resource for businesses. However, machine learning requires standard operating procedures to be established. An example machine learning business integration process is shown here, where the critical first step is data curation. Then significant work by machine learning engineers and data scientists is required to develop optimal machine learning models. The training and validation of machine learning models is its own sub-cycle to produce an optimal model. With the trained machine learning model in hand, it needs to be handled like any other new software component, including systems integration, testing, deployment into production systems, and then continual modeling and evaluation. One of the biggest challenges facing businesses is the variety of data, where they have traditional data repositories such as database systems, as well as huge archives of other types of data. For example, companies may be collecting sensor and system diagnostic data or social media data. All of these disparate data sources represent data of differing veracity or trust levels, and the availability on variable or irregular schedules of this data presents another challenge. To exploit this diverse data, many companies are augmenting their data warehouse strategy into data lake concepts. This has an advantage for machine learning in that the data can be extracted and transformed as needed for different machine learning systems. There are numerous types of machine learning, such as unsupervised and supervised machine learning, and derivatives of each. While this hierarchy is a drastic simplification of the rich field of machine learning, it gives some context to map concepts. Unsupervised machine learning, such as cluster analysis and data mining, do not impart knowledge or known facts or answers into the machine learning system. Instead, the machine learning discovers key salient artifacts in the data. It is then up to domain experts and stakeholders to analyze those findings. Supervised machine learning, on the other hand, requires that knowledge be given to the machine learning system. That is to say, we tell the algorithm both the input and the expected output. It is critical to employ machine learning engineers and data scientists that know how to select appropriate techniques and optimize the right machine learning approaches for various business processes. You will recall the last step in the machine learning business integration process was to monitor and evaluate. Businesses must leverage existing key performance indicators and develop new measures for machine learning augmented business processes. Management of the business should be asking questions such as how are business processes measuring against key performance indicators before and after the integration of machine learning, and how are the machine learning components performing in regards to the model performance metric. It is critical that data going into the machine learning enhanced business processes are continually monitored for potential data drift issues that may need to be addressed. Furthermore, deployed models and systems should be evaluated to determine if the models are exhibiting biases that disadvantage your operations or the customer experience. These are critical concepts that must be understood and addressed for machine learning deployments. Most of the modern machine learning techniques use data in the form of giant numerical matrices and vectors. These numerical structures and the mathematical operations performed in most of the machine learning algorithms are not well suited for traditional computer CPUs. Thanks to the explosive growth in graphics processing units, or GPUs, that are designed from the ground up for streams of matrix and vector math operations, we can augment the typical computer servers in our data centers with coprocessors. The numerical matrices and vectors are often referred to as tensors, and hardware may also include specialized tensor cores or even tensor processing units available in some commercial cloud environments. Often, because of the scale of the data needed to build robust machine learning models, the complexity of the models and the amount of computation needed for the models to learn is necessary to leverage significant computing resources. These resources may be a local on-premise computing cluster, which is a tightly coupled group of servers, often augmented with GPU coprocessors that can work together to accelerate machine learning model training and inference. Another option is to scale machine learning into cloud environments, where the upfront cost for scaling computation is minimal compared to the time and human effort to build a new cluster on-premise. Cloud providers facilitate use of GPU coprocessors linked to the cloud resources, and some provide TPU or tensor processing units as well. One of the best technologies to leverage for machine learning are containers. A container is a definition of a computing environment that can be isolated and replicated on various hardware. In many situations, a machine learning engineer will develop a container to prototype machine learning models. That container can be replicated from the engineer's laptop to a local cluster, and hundreds of the container image can be brought online and connected to high-capacity, high-speed data storage for training the machine learning models using very large data sets. This is critical for techniques such as hyperparameter search and optimization and training and validation cycles. Containers can also be replicated to the commercial cloud providers as well. In the case of the final production machine learning model, it can be orchestrated into a container and replicated across both cloud or local cluster deployments. Technical business professionals must have an understanding of machine learning, including how it is implemented in the business environment and how to manage both the input and resulting data from machine learning components. We have developed a 5-course series on leveraging machine learning for business operations. The courses provide an end-to-end perspective for machine learning in business. We investigate business applications of machine learning, specifically related to decision making, and we provide an in-depth knowledge of the collecting, analyzing, and interpreting data using machine learning and how this can benefit your business. This course series will help business managers understand machine learning and how it can be leveraged for the benefit of business operations. The 5 courses include Machine Learning in the Age of Big Data, which examines the concepts of big data, the various attributes of machine learning, the different types of machine learning, and a lot of the key concepts that lay the foundation for the other courses. Machine Learning in a Data-Driven Business Environment, which investigates how machine learning can be integrated into data-driven businesses, how it can be used to augment existing business practices and business operations, and the right techniques to deploy this. Course 3, Sound Business Practices for Data Mining and Predictive Analytics, drills down into the key elements to integrate machine learning into business practices, such as measuring the key performance indicators, how to develop new key performance indicators relative to machine learning, and compare and contrast machine learning enhanced business processes versus original business processes. The 4th course, Machine Learning, Algorithms, Models, and Systems Integration, gets into the technical details of various different machine learning algorithms and models, understanding the difference between what an algorithm is and a model, and how to take developed models and perform a rigorous systems integration into business processes. Course 5, Deploying Machine Learning Platforms and Technologies and Tools in Your Enterprise, addresses the technical needs regarding getting the machine learning models deployed, how to train models, what technologies are good for the data management, what platforms are suitable for training versus inference, including cloud and cluster and container deployments. You can learn more about these courses by following the links below. And this, I apologize that I seem to have went very, very fast on this one, which will leave us plenty of time for some questions or some Q&A.
Great. Thank you very much, Grant. We really appreciate this talk, and it does leave us time for questions. And so we'd like to encourage people to go ahead and submit them in the Q&A box on your screen. First question will be, how long have you been working in this field, and what are some of the things that you enjoy most about the challenges of this new technology? Oh, Grant, maybe on mute.
I was moving windows around to find the unmute button. Sorry. Right. So that is a great question. I've been doing machine learning ever since graduate school, and early on in graduate school, one of the things that I faced was the challenge of scaling machine learning up to massive amounts of data. I specifically spent a lot of time in the realm of computer vision before the deep learning thrust that we're currently in, a lot of the traditional computer vision algorithms, and trying to figure out how to scale them up from, with their approaches that are all machine learning oriented and image processing. How do I go from where people are developing these sorts of algorithms on images that are 256 by 256 pixels up to satellite images that are a billion pixels or a couple billion pixels, and not just 3 bands of color, but or 8 bands of color. And so I've spent the last 15 years working in that problem space very heavily, and then utilizing a lot of different machine learning techniques since then on data that even bridged out from that more traditional non-vision data, other types of sensors as well. So it's been fun. The good thing from my perspective is that with machine learning and both in the research side and also talking with people that I interact with from the business world, there's no end of the possibilities. One of the things that I've been fortunate enough to do is as the director of the data science program at the University of Missouri, I have an industry advisory board that I talk with a lot about data science. And one of the themes for the last 5 years has really been machine learning and AI and integrating that into business and listening to how these business leaders are leveraging machine learning and adapting their business processes using machine learning, kind of learning from them what the businesses are doing, sharing with them some of the ideas from academia, and having that feedback cycle has actually been really, really helpful for me to really get a good idea of how to help coach both data science trainees, computer science graduate students, alumni that come back from industry with some questions, seeking some guidance, as well as some of these discussions with business leaders that I have on a regular basis.
Super. Thank you, Grant. We've got lots of questions coming in now. Are there one question from Lawrence, are there different standards for data storage, for example, bit placements, et cetera, and how are they used to work with data?
Different standards for data storage. That's a really broad area that is usually addressed from the perspective of a data engineer working kind of in conjunction with a data architect, who then is going to also have in this kind of a cross-functional team a machine learning engineer or a data scientist. And so there's a lot of opinions out there, and I'm not going to say that mine is necessarily right or wrong. And so we mentioned in the webinar, and there's a lot of details in the course series about data warehouses versus data lakes. There's a lot of different opinions on which ones are better. There's various different trade-offs that we talk about. One of the things that a lot of companies use with the data warehouse is they've got to do a lot of unfolding, and they're adding redundancy to data to make layers line up and stuff like that. They're making decisions before to kind of ease the building of reports downstream, which is not always the good thing from a data storage perspective for machine learning, where you may do some data massaging to get it into a data warehouse that actually reduces some fidelity of the data that a machine learning model may need or may want. When it gets down to from a lower level before I jump there, the data lake concept is trying to keep the data in the very raw form and being able to have a series of ETL or extract transform library load functions that operate as needed, kind of a just-in-time extract from the data lake to curate a bunch of machine learning data into the optimal form with minimal transformation so that you can have some provenance of going from that raw data all the way through the end of the machine learning model in your machine learning business process in terms of the training and development. If we go down to the more technical, where someone talked about where bits came up, most machine learning engineers aren't going to be concerned with bit level storage of that. Really, they're looking at what is the format of the data. Do I have it in numerical formats? Is it packed up and compressed somehow? Has it been transformed into character data that I've got to read and parse and then turn back into numerical data? And those are some of the trade-offs that businesses, the data architects, the database administrators, the data engineers, and the machine learning engineer or data scientist need to all kind of have as discussions from a team perspective to make sure that they're not handicapping the machine learning models by doing early data transformations or manipulations that lose some data statistics or fidelity in the process. Hopefully that answered the question.
Thanks, Grant. We have another one from Alan. What math knowledge is required to understand and use machine learning? And more importantly, what do you recommend is the best way to relearn that knowledge?
Could you repeat what was the knowledge? What knowledge?
Mathematical
NAS?
knowledge.
Oh, math knowledge. Okay,
yeah,
sorry.
Math knowledge is required. Mm-hmm.
Yep. So that's a great question. So one of the key things that I think from my perspective is having a basic if you want to be a machine learning engineer, you need to have a good understanding of linear algebra, and that is your starting point. That is, how do we do math on those vectors and matrices, those numerical vectors and matrices that we talked about. That is the majority of the format that most of the machine learning models are using. That is your most foundational key. Depending on where you're going and how involved you are, it's going to be very good for most machine learning engineers to understand the calculus behind optimization of some of these machine learning models. So we also need some basics from multivariate statistics as well. Those come into play when you start looking at things like decision trees and information theory related to random forest and stuff like that. Now, if you're a business manager, understanding just some of these basic concepts and what they're doing, you don't need that in-depth, deep technical knowledge. You don't need to know how to hand compute, say, an eigenvalue from a matrix. If you're a manager, you need to know what are the characteristic performance, like how does a model work and why does it do what it does? The machine learning engineer needs to know why the model works at a little bit more deeper level so that they can provide the guidance. So they can, when they start evaluating model prospects for a machine learning task, they're not starting going in the wrong direction. They're looking in the right direction. So it depends on how deep you are involved in things. So as I started, I think the most important thing is to start with a refresher on linear algebra, then begin to look at some of the basics of multivariate statistics, and some of the basics of the calculus that's used for optimizations. Depending on what your tolerance is for math, some people love it, some people just want to use the cool tools. It depends on how far you dive down. And then the reality is most machine learning engineers at this point that are working in businesses are not reinventing the wheel. They're using the cogs that are on the shelf, they're pulling them together, they're building the machine from the prefabricated parts that are in the software packages, the things that have been tested and proven to function correctly. And then in that case, when you're not building your own machine from scratch at the machine learning level, that in-depth knowledge is only really necessary for background context. So hopefully that answered your question.
We have another question, just sort of adding on to that. If a business doesn't have the resources or employee expertise to fully dive into machine learning applications, how would you suggest they start smaller?
Let's see. So I think what you need to do, if you don't have the expertise and the resources to go in kind of with both feet diving in the deep end, I think the best thing to do is start with two people. It can't be kind of a one-person thing. The first person would be the business functional stakeholder. Who's the person that's not going to do the machine learning stuff or the exploration, but understands the most about the value to the business and how it can reshape the business. And then you need, as a second person, the technical person that can begin to explore, self-learn, and prototype and kind of get their head wrapped around the art of the possible. And so that they can come and share that with the stakeholder, and the stakeholder can ask the questions, offer the guidance, and that small little team of two is probably really all you need if you're small and you're resource constrained to start to build a little bit of momentum, to understand the art of the possible, to maybe prototype or proof of concept something small. There's enough resources out there on the web in terms of free computing resources. There's a variety of resources out there between things like Kaggle, Python Anywhere, all sorts of systems out there, free usage tiers from cloud providers, where you don't need an upfront investment to begin to dabble into this. So I think that is a way to start really small, but the key is that you can't have two technical people doing it on their own. When it comes to doing stuff in business, you have to have the non-technical business person with that functional stakeholder that can keep pulling the technical people back into the business relevant world.
Thanks, Grant. Here's another one from Arcana. Can machine learning help in the application of AI without using deep learning?
Absolutely. So, just as a clarifying sort of element, AI is a very broad term. We see it in headlines all the time now. It's changing everything. The majority of times we see it in headlines, that particular flavor of AI is data-driven machine learning. Now, there are other types of AI, and not all machine learning necessarily someone would call AI either. So it's a bunch of kind of overlapping circles, if you will. But not all revolutionary machine learning that is AI-like requires deep learning. Sometimes simpler is better. One of the most common things that you see in a lot of industries is they do not want to look at deep learning because it's currently in a state of challenging interpretability. They want to know why a machine learning model makes a decision, why it did some action. Why did this AI do this? And that's where deep learning currently has kind of a giant gap in making everyone happy. Is it's too hard in most of these deep learning models to fully understand and intimately why a model does something. So people look at things like decision trees and random forest, where you can unwind those and you can look at why they're making decisions. Some of those other ensemble methods that exist out there that aren't necessarily deep learning. So there's a lot of options that aren't deep learning, and the majority of people that like those, well, there's a lot of reasons why they like those, but one of the big drivers is interpretability. Being able to kind of take the lid off the machine and see why was it making decisions. Because with existing deep learning, and with all machine learning, the model, you need good, representative, robust data to build a robust model. And it's one of the things that we talk about in the course series is the need for really in-depth data curation and exploration before you ever start building machine learning models. So that you understand, what data do I not have? Do I have data gaps and stuff like that? With deep machine learning, sometimes it's hard to understand where the data gaps may have led to learning gaps in the machines. So there's definitely some good, successful machine learning out there, coming from things like random forest. People still use occasionally support vector machines, and a variety of other things. And then there's a lot of the unsupervised machine learning that's really, really valuable to businesses and generally is not built around deep learning.
Great. Here is another question from, I apologize for the pronunciation, but Cooter. Adoption of machine learning models requires interpretability and transportability. Non-interoperable is a major barrier to model transportability. How do you leverage the prediction model and assess its transportability to enhance business operations?
I'm gonna have to get my notepad to start taking notes for these questions. So let's talk about the transportability first. So I'm looking at transportability. I think there's two ways to look at it. Can I take a model and can I move it and can I run it other places? Can I transport it someplace and does it work in other places? This is where I think containers are of critical importance in modern machine learning, and as part of having a well-developed machine learning model development workflow. So that when you have a model, you can serialize it and then you can stand up that container and the model will work on any hardware. The caveat of that for any model that you've deployed anywhere is going to be that you need to ensure that your data that you train with and that you validate with and that you test with before you deploy, you need to ensure that that data, the characteristics of that data actually truly match the characteristics of the operational data. Otherwise, your model is not going to port well from development and validation into production. Let's see. The challenge there, which also gets into the interpretability, is depending on the model and depending on what you've done up front to understand the data characteristics significantly enough, you may not be able to interpret why the model performs more poorly in a production environment. You know, when you said, okay, well, I've had this nice data set, I prototyped the model on my laptop, I moved the container up into my local cluster and I ran hyperparameter grid searches, looking at a couple different machine learning pipelines and data conditionings and feature reductions. And I produced this production model. I deployed the model up in the cloud, and all of a sudden the model is operating at only half of its, you know, for instance, maybe half of its F1 score when I look at it in the real world. In a lot of cases, understanding why that happens goes all the way back to understanding the input data and understanding the provenance of what someone is doing to condition the data for training versus are they doing that in a very repeatable fashion to condition the data for inference up in a production environment. So I may have talked around some of the, hopefully I hit all the elements of that question.
Thanks, Grant. Next question from Harry, who says his company is retired. So congratulations on your retirement, Harry. Question is, who are the biggest users of machine learning?
I'm sorry, what was that one?
Who are the biggest users of machine learning?
Oh, that's okay. So that's a great question. I think the most important question, or the most important answer to that question, is you have to look at machine learning from two different perspectives. One are who are the people that deploy machine learning the most for their business processes, and then the other side is who are the people actually affected by the machine learning. Everyone that is interacting with technology nowadays are the biggest users of machine learning. Every time you pick up your smartphone or you do stuff on the internet and you interact with web applications, social media, stuff like that, you are being used or you are using machine learning behind the scenes in some fashion. When you drive modern cars, you are using machine learning. You know, the example I love is a few years back, my wife got a nice new Honda, and it had that adaptive cruise control, and it's got a camera that basically sees when a car moves in front of her and lets off the gas for the adaptive cruise control. That's a use of machine learning, which, you know, and then we've heard about how social media companies are using machine learning, you know, to analyze people's pictures and to analyze people's text and to try to auto filter things that people post on social media. we've all seen how industrial manufacturing has been revolutionized by robotics, and those were originally precisely programmed robotics. Well, now things are going all the way to where you've got computer vision and machine learning doing rapid quality assurance and defect analysis and stuff like that. So the big users are pretty much every business that is operating at scale and wants to produce more efficiencies. They are adapting machine learning. So obviously the tech companies are huge users of machine learning in terms of their production and what they're doing. But everybody that's a consumer with any interaction with electronics, they are consuming in most cases some result of machine learning, and at the same time that all that digital trace data that we produce as a society is input into more machine learning algorithms used by all those businesses. So I don't think there's any one industry that's necessarily leading. There are probably some industries that are dragging behind because of kind of goes back to one of the earlier questions, the level of trust that they'll put in a artificial intelligence or a machine learning model versus human trust. But I think everybody in every business really is pushing forward. And that's why this course series is so well timed, because if you're a medium, and if you're not a tiny little small business, if you're medium and larger, you need to understand how machine learning is changing things. Because if you don't start adapting machine learning techniques the way all of your competitors in your business space are, you're going to be left far behind.
Thank you. Another question, are there any examples of implemented machine learning models that are currently used in business operations and are successful in predictions and have a good impact on workflow decision making?
Yes. Yeah, there are definitely instances. So one of the things that I kind of hit on a little bit is when I running my data science program, I talked to a lot of my industry advisory board members, and I'm talking to their lead data scientists or their chief data analytics officers. So sometimes you can find some really interesting things out there. The majority of the time, they don't get into the details, but they are utilizing machine learning and AI in all manners, all of their business stack, from source materials all the way through the output, whatever the industry is. One of the case studies that we look at, for instance, in the course series is the UPS Orion system. Their on-road integrated, I can't remember what the acronym stands for off the top of my head, but helps them basically solve the daily traveling salesman problem for package delivery optimization, minimizing miles and time on vehicles. So there's a good in-depth dive on that. I know I've got industry people that I've talked with from the healthcare industry that are looking at a variety of things, such as analyzing prescription patterns with machine learning to discover trends or discover outliers, looking at like food systems. So I do a lot of research in a defense and security space, and there's a lot of use there. So there's a lot of places where people are using it. Usually you can find a couple good case studies. One that's in the course, we dive in and we look at the Orion system from UPS. And usually you can find a couple of those out there. So definitely some cases where people are using it extremely successful to make predictions of things. If we talk about like just specifically any business that sells something off of their shelf, that has shelves of things and sells it, the majority of those large chains have gone to predictive analytics and prescriptive analytics to control just-in-time delivery of things that need to go on shelves, to minimize the amount of the backlog of stuff in storerooms or warehouses, to kind of optimize the from the source to the product on the shelf and minimize the time it's on the shelf. So there's a lot of good use cases, or got a lot of good examples floating around out there. Some of them, they don't talk about how they do it because they want to keep that as a trade secret. And some of them are very kind of shy about talking about how good they're doing. But from my discussions that I've had with people that I can't dive into the details, some of them are doing really phenomenal at utilizing machine learning and predictive analytics in this manner.
We have another question from Michael related to the course, the material in the course. Does it include information on the technology of Kafka and or Kafka streaming, more specifically, how this technology can be used in the context of enhancing business operations with machine learning?
So the way the course is described is it doesn't anchor down into any specific tool. It's more at the conceptual level and how the concepts fit together. One of the things that we hope to get out of this course is that businesses and business leaders can understand this context of business operations and machine learning together, and then internally with their machine learning engineers, their software developers, their systems engineers can make the right technology choices that are appropriate for their business, because there's going to be plenty of businesses that already have a very significant investment in some platform or other, and then they need to really understand, well, okay, we're locked into this platform because we've got 15 years of institutional buy-in and data. So what is the thing that we can bolt onto this? And so there's not a lot of dive into specific platforms, more conceptual level.
Thanks, Grant. Parv asked, what are the different fields which are not using machine learning now, but can make great use of in the future?
So I think one of the fields, some of the areas where we're not seeing it used as widely now as we would in the future is in the care of citizens, either healthcare or people think of healthcare as doctors, but there's a broader spectrum of taking care of people. And so I think there's a lot of opportunity there. I think one of the issues is there's a lot of things, there's a lot of barriers that people have to not necessarily overcome, but work around in a proper way, for instance. So when you start talking about data related to people, one of the things that always makes the news is when someone abuses data about a massive amount of people to then do predictive analytics. That's not a good thing. So when you see the industry built around the care of people, you have things like in the US, you have HIPAA regulations that protect people's information and the use and release of it. You have a lot of ethical things, and from research institutions, you have institutional research boards to kind of protect people. So I think I think that area is a little bit behind employing the machine learning because of the protections that are in place and coming to grips with the potential consequences. We probably in my field, we've all heard about how machine learning models with improper data or not the right mix of data develop a bias, and they make bad decisions, or they make bad predictions, or they learn to do something they weren't intended to do that biases or disadvantages the population. So there's a lot of caution in that area, but there's also a lot of promise. A lot of the other areas, a lot of the other fields don't have that ethical human care component that they've got to be super careful of. And then we see other industries that probably push forward too fast with it. We've all seen the media reports of social media utilizing machine learning and algorithms that do all these different things and have negative consequences for society. So there's overly cautious, and there's not cautious enough, and there's everything in between. And I think that's what's kind of driving where different industries are with their deployment of machine learning.
Grant, we have a question from Neza. She asked, how can machine learning help us in education?
Oh, that's a great question. So education, I'll tackle it from kind of a I'll say primary education perspective. So there's a for instance, and there's a lot of times where we try to overly reduce students in, say, primary education to grades or to scores on tests. The reason we do that is because that's a simple model. Someone can understand it. So in the U.S. here, I've got a college applicant coming in as a freshman. I may want to look at their ACT score and say, well, okay, these sections, they got these scores. That is a very naive model of who they are as a person intellectually. Overly naive, some would argue. Machine learning techniques may be able to develop better models of analyzing a person and do better at recommending where mitigations for learning need to be applied, or interventions, I think is the term in that field. So they may be able to detect, earlier developmental issues, learning development barriers and stuff like that. The thing, again, this gets into, you have to be careful that you don't have machine learning models that are building in biases and therefore disadvantaging subpopulations. There's, on the flip side, or on kind of the other side of that, I would say one of the really useful things that I've seen is there's been working backward from high school, from kind of high school or secondary education through middle school and stuff, is getting students more data literate. One of the things that we think of when we look at society is what is the literacy rate of a society? That's an important metric on how learning is handled in a society. Well, and we talk about written literacy. Data literacy, I think, is one of the things that's going to become a very, very important concept in the future society. How well can children coming out of school understand data? Because data is thrown at people all the time in society, and most people aren't fully equipped to kind of understand data literacy. And then when we start seeing more and more machine learning and AI doing things for people, having that data literacy, and even some of those concepts begin to seep backward from college level courses into high school and then even lower, I think is going to be an important trend that we see, and should be an important trend. So I don't know if I answered the question as ideally, but I answered it as best I can.
Thanks very much. We got a question, a few more. What are some barriers that might hinder business leaders from adapting machine learning?
Barriers that inhibit business leaders from adapting machine learning. So I think it goes a little bit to someone else's earlier question, is what if you don't have the resources to really get into it, to dive in with both feet? I think resources and I think resources is one of the things. And so if a business leader doesn't have the resources to do it right, or doesn't have the human capital, which is the most important element really, then that's going to be the biggest barrier. When it gets to the very top, that's the business leader with all the resources of the business, and they need to understand, if you're a business leader underneath the very top, how to convey and how to compute the return on investment for machine learning. What is both the short-term and the long-term benefit to the business to get yourself more resources? And that's one of the things that overcome the barrier. And the most important resource for any machine learning business deployment is the person element. You can have all the fancy hardware in the world, but you need to have a machine learning engineer or a data scientist and a data architect and data engineer, you need to have a team of people and business users that work across all those functions to understand how to get the raw inputs to the machine learning to turn into something valuable to the business. That human element, not having that human element, I think is going to be the biggest barrier for a long time. If you believe the ads that you see on social media, there's hundreds of thousands of existing openings for machine learning engineers, for data scientists, for advanced data analytics people. Hundreds of thousands of job openings just in the U.S., and it's expected to continue to grow. That, to me, is going to be one of the biggest barriers that businesses are going to face, is finding good people, fitting them into the company culture, and then getting them to provide value from by integrating machine learning into business processes. So I guess hands down, the biggest barrier is going to be finding the talent and kind of solving that problem.
Mm-hmm. Thanks, Grant. We just have a couple more minutes left, and we've got a few more questions. When KPIs may not be available, how would you recommend finding KPIs from a machine learning perspective? Can machine learning be a KPI?
That is an excellent question. So we dive down into that a little bit in the course, or actually a good chunk in the course. So just to recap for anyone coming from a technical and a less business side, KPI is a key performance indicator. A real simple example is, what are my increased sales year over year or month over month? That is a quantitative thing that I can look at. I'll have a goal. I'm either hitting it, I'm exceeding it, or I'm deficient. And it says, this is how I'm doing, this is how my business is doing, or this is how my unit's doing. Now, if you don't have those well established, you're at a little bit of a disadvantage. One of the things that I try to hit on in the course is thinking about establishing key performance indicators if you don't have them, and that they really, when it comes to a business process, the very first thing that you should do when you say, I want to incorporate machine learning into this business process, is identify any and all key performance indicators that you can for that process, and then start to measure them before you start your development of the machine learning integration. Because you need to have a baseline understanding of how are things going before machine learning. And then once you bring machine learning in, now how did those key performance indicators change? You absolutely have to develop those right off the bat to do machine learning correct, in my opinion, from a business perspective. The other thing is, even with those base business KPIs, you need to develop additional KPIs that are centric to the model and centric to the component of the business that's utilizing the model. So a sense of correctness. So if you've got a machine learning engineer and they're doing model training and they're doing some training and validation, trying to find the optimal way of producing a production model through a smaller data set, they're going to have some metrics of the model. Like if it's a classification model, they may be discussing precision, recall, F1, confusion matrices and stuff like that. And those represent metrics of the model. Those metrics of the model translate into some sort of business performance when the model is actually integrated. And so understanding those, or even taking live business data on a regular basis and pulling the model aside and evaluating it and producing those model level metrics, that is key. And that's one of those things that I hit on with that pipeline of saying the constant monitoring is the most important. So you have to develop KPIs before you ever start as best you can. And then you have to keep measuring them all the way before development, through development, and then even after integration to see how they change. Is the model making a difference? Hopefully that answered that question.
Thank you. Thank you very much. We have unfortunately come to the end of our time here. It's gone really fast, actually. So I'd like to thank everybody who came. And for those who submitted questions, we really appreciate it. As noted earlier, the on-demand link for today's event will be emailed to everyone in approximately 2 hours. You'll be able to see the slides as well. And before you leave, if you could please complete our feedback survey via the survey tool at the bottom of your screen, we would really appreciate it. And thank you, everyone, for participating, and thank you, Grant, and have a great day.
Thank you.